Good morning everyone. Thank you for joining me in this video. I am Mr. Ish. Today I want to do this topic on hyperbolic integrals because when it has come to integration, I've done the polynomials. We've looked at the trigonometric integration and exponential functions, power functions. Lastly, we've also looked at natural log. We haven't looked at hyperbolic yet. I just want to bring up this topic on hyperbolic integration before we get into those substitution techniques. Hyperbolic functions are not very commonly seen in terms of integration, let alone in terms of derivation as well. From my experience, I just don't see too many of these. Now, with regards to integrals of hyperbolics, there are basically 10 that I want to show you. You know, if you're doing the integration of sine hx, you should end up with some function over here. It would be this, cosine hx, because when you do the derivative of this, you end up exactly back where you started. That you could easily put them into memory right when you see them here. Look, if you're doing the integration of cosine hx, you should end up with an antiderivative. If you take the derivative of this, you end up back to the original, and you know this can be nothing else other than the sine hx plus c, or hyperbolic sine for this and the hyperbolic cosine for that. So these two are the easy ones. The next two which I'll present to you are relatively easy, but then after that it becomes relatively tricky. Relatively tricky only in the sense that they're more difficult to memorize. But you don't have to memorize. Like I said, you never have to memorize any of this because reference sheets are always there at your disposal. The next one we want to look at is this one. How about this one? Hyperbolic tangent. You're coming up here with an answer such that if you took the derivative of this, you should end up back over here. Natural log hyperbolic cosine h x plus c. You see? This right here ends up being the antiderivative of this. Why? Because when you do the derivative of this, you end up back over here, and I can show you that very easily. If this right here is your composite function, you know you have to substitute using the chain rule. If u is equal to hyperbolic cosine, then f of u is equal to ln u. And then derivative of u with regards to the x is hyperbolic cosine hx. When you run this through, you end up getting 1 over u. As you know, as a derivative for a natural log, 1 over u. The derivative of this is a sine hx. When you resubstitute back for the u, which was hyperbolic cosine, you get sine hx in the numerator divided by hyperbolic cosine hx in the denominator, which you know very well translates into a hyperbolic tangent. So we know we are good. So this right here is not too hard, but you have a natural log playing in over here. For this hyperbolic cotangent, you can imagine it would be something similar to what you've seen, except you will have this sine hx. The first two, the hyperbolic cosine, hyperbolic sine integrations are easier. The next two, tangent and cotangent, are relatively easy because you have a pattern which develops over here, the natural log pattern, because when you do the derivative of these antiderivatives, it's very easy to come back to the original parental function right over here. If you do the derivative of this, you know you're going to do the chain rule. You'll do ln u, and then you do the derivative with regards to your substituent, the x variable over here, sine hx. When you do the derivative of this, you get 1 over u multiplied by cosine hx, and you get cosine hx followed by the resubstitution of the u, which is sine hx, and you know this right here is right over here, the hyperbolic cotangent. So you are getting the derivative of your antiderivative, leading you back to your original function. Remember, all of this is the basic essence of that fundamental theorem of calculus. So those are 4 we've presented. We have 6 more to present. Now, when you're looking at the hyperbolic secant, it has one of those derivatives which is, for me, very difficult to memorize and remember. So I always have to refer back to my cheat sheet or my reference sheet. When you look at the integral of this or the antiderivative, you get something which is rather messy in appearance. It's tan, inverse tan, and you get sine hx. You're basically getting an arctan. The arctan of the value or the variable which is being affected by the arctangent function is sine hx. And then you know you have a plus c because these are all indefinite integrals. You can imagine how this would play out in terms of doing the derivative of this antiderivative, and we can do it. There's nothing wrong with us testing ourselves. If u is equal to sine hx and f of u is equal to arctan u. Let's write it out as arctan u, and now you know here you have to remember the derivative of arctan. Then the du or dx is just sine hx, which is easy. The derivative of arctan u is always in the form of 1 over 1 plus x squared, but here x squared happens to be a u square, right? And then over here, what do we have? Sine hx becomes cosine hx. What do we get? Cosine hx over cosine hx is multiplying by this 1 and eliminating the 1 and staying as a cosine hx. You get 1 plus u square, but u was originally sine hx, so you get sine h square x. This has to somehow transform or algebraically change into that. If you think very quickly back to one of the identities, hyperbolic identity, cosine h square x minus sine h square x is equal to 1, the parental identity from which you can derive the other ones. And I've presented this and stressed this too frequently enough that it should not be ignored. Think about it. If you are to manipulate this such that you take and you solve only for the cosine h square x, you'll take the sine h square x onto the other side and you get 1 plus sine h squared x. And you know this right over here, when you see it, can be substituted for this, and that's exactly how this plays out over here. By means of a simple algebraic manipulation and substitution, you get cosine hx, which is in your numerator already. All of this gets substituted by cosine h square x. When you do the simple simplification over here, you end up with cosine hx over here on the bottom, right? Because this one cancels out with this exponent over here, and you know this translates very easily into our original function, and that's how you demonstrate this integration technique and the antiderivative that it produces, and then the derivative of this antiderivative going back to the original function by means of this procedure. But this procedure was only dependent and realized if you could remember this original identity. For this one, hyperbolic cosecant hx is a very messy one in terms of taking the antiderivative back to the original function. But if you look at this right here, you'll get something which has the appearance of this natural log tangent h x over 2 plus c. If you were to take the derivative of this and take it back, you will take your antiderivative to your original function. But doing this procedure from here to here is difficult, it's cumbersome, and we don't have enough space here on the board to do it. The next one right over here is not hard. You know, you saw something like this with regards to trigonometric integral. When you're looking at this, you're thinking about tan hx plus c. If you take the derivative of this antiderivative, you'll come back over here and you can show that very easily. And you can imagine why it's easy, because you're looking at the hyperbolic tangent as a hyperbolic sine or hyperbolic cosine, and then you have to do the quotient rule over here. G function, f function, you do the g function multiplied by the derivative of the f function, right? And then you have to do the f function multiplied by the derivative of the g function over the g function squared. This part right here in the numerator is easy because the derivatives of these are very easy. You'll basically get derivative of sine hx is cosine hx. You'll get cosine hx squared here on the top. Derivative of cosine hx is sine hx. You'll get minus sine h squared x over cosine h squared x. Now think back to that very all-important hyperbolic identity I've presented, where cosine h squared x minus sine h squared x, this right here in the numerator, is technically equal to 1, right? The entire numerator is equal to 1 by means of that identity. You get 1 over cosine h squared x. 1 over cosine h squared x is the same thing as saying secant h squared x, right? Because this right here is the same thing as saying secant h squared x. But we have to remember this identity right over here, that this thing right over here is equal to a 1. So a few more of these hyperbolic integrals to introduce you to, then we are done with the development of these antiderivatives over here for you. When you're looking at this, right, your antiderivative is going to be minus cotangent hx plus c. When you do the derivative of this antiderivative, you'll end up back to this, and we can show that to you. It's not a difficult process by any means. You're just going to be bringing the minus outside, and you'll view this in terms of this cosine hx over sine hx. You see, because this right here will equal to hyperbolic cotangent. And you know you have to use a quotient rule over here. We'll do sine hx multiplied by the derivative of this hyperbolic cosine, which I haven't done yet, but I will. The f function multiplied by the derivative of what will be the g function all over the g function squared. Do the numerator, you're going to get a minus sine hx times the sine hx, you get a minus sine h squared x. Here you get a minus cosine hx times that. You're going to get derivative here, it will be a cosine hx, you'll get a cosine h squared x over sine h squared x. You can open up this in the numerator, you end up with cosine h squared x minus sine h squared x over sine h square x, and you know this right here in the top is equal to 1. You get 1 over sine h squared x, which you know cosecant h square x, just by means of the basic definitions we know over here. And this one over here is done, not a hard one by any means. This one over here very well mirrors one you've seen for trigonometry. Integration of this hyperbolic function over here, you're going to end up with minus secant hx plus c. Here you'll have a minus. In the trigonometric version you didn't have a minus. You're going to do the derivative of this by taking the minus outside, and you're going to view this secant hx as 1 over cosine hx. And you know here you're doing nothing more than the quotient rule. You're doing the g function multiplied by the derivative of the f function. The 1 will zero out, and the f function multiplying by the derivative of the g function, right, all over the g function squared. When you do this, it zeroes out because the derivative of a constant is always 0. This zeroes out this entire part. We can hit this minus with this minus and open it up. We'll basically get over here on the top the derivative of the cosine, which will be sine hx. That's it. Because the minuses cancelled each other out. Minus times minus was a positive. And you get a cosine hx over here times 1 over cosine hx. And you can imagine this takes you back over here. You have a tan hx, you have a secant hx over here. And you have exactly what you started with right here. This right here, this is the second last integral I wanted to show you. This hyperbolic function integral is not hard to remember, because it very well mirrors exactly the similar one. Remember, the cosecant x, cotan x integration led to minus cosecant x. But the hyperbolic version leads exactly to the same thing, except you're having here the presence of these h's, the hyperbolic. It's exactly mirroring the trigonometric version of the same function integral. Anyhow, let's do the derivative of this antiderivative, and we'll end up back over here, and your antiderivative as this sine hx, and then you know it's basically just a quotient rule over here. You'll do the g function multiplied by the derivative of the f function, and the f function multiplying now by the derivative of the g function. Many of these steps can be eliminated and done entirely in our head. This will zero out. The minus and the minus will become positive. You'll get over here the derivative of the sine hx, which is just cosine hx, right? Or sine hx squared, but we're separating it out like I showed you earlier. And then when you do this, you get cotangent hx, and you get cosecant hx, and you end up back to the original function, that is the derivative of the antiderivative. The minuses are easily being dealt with by this minus and this minus cancelling out, and we're done with this. So this is the introduction of the hyperbolic function integrals that we need to know. For the purposes of calculus, we're not going to go into the inverses of any of these, because inverse hyperbolics are just too infrequently seen. But next we'll just be looking at various types of questions. So let's put some of these integrals to work over here. We have a definite integral question, interval 0 to 1 for sine hx, and we have to find the numerical answer for this. The numerical antiderivative for sine hx shouldn't be too hard. Now the problem will arise when we actually do the calculating part, and we'll talk about it when we get there. The antiderivative of this is easy. When you do the integration of this, you just follow the definition as you already know, and this will lead you to this antiderivative over the interval. This essentially what you're doing now over here is cosine h1 minus cosine h0. Now you cannot confuse this for the cosine function, because it isn't. It's a hyperbolic cosine. You have to be able to evaluate the answers for each of these portions of this process over here. Now the problem, as I was hinting to before, arises if your calculator such as mine does not have hyperbolic functions. It just doesn't have it. So now we have to actually do a little bit of work to get to the numerical answer, which is fine. I don't mind it. We'll have to think back to the definition of the hyperbolic cosine, and where we have the x's in that definition or in the formula, we'll put these ones and zeros. You'll do e to the power 1 plus e to the power minus 1 over 2. This is the hyperbolic cosine function definition of the 1 plugged in, minus e to the power 0 plus e to the power minus 0. Minus 0 is kind of meaningless over here, and you'll calculate this out. When you calculate this out, all of this is done separately. You'll get a numerical answer. All of this is done separately. You minus the 2. You'll have to do it that way. This over here, you'll get 1 plus 1 over 2. This right here will translate into a 1 over here. We have to get a value over here, and you can do it. Work from the right towards the left. What I'm getting over here is 1.543 right here. 1.543. When you minus 1 from here, you get your final numerical answer, which is 0.543. And basically the most difficult part in this question is not this integration part, because the formula, the reference sheet tells you exactly that. It's this part over here if you do not have this function on your calculator. And here's a very similar question, except here you're looking at this function and you have to find its antiderivative. Either your memory or your reference sheet will tell you exactly what it is, and it's going to be sine hx over the interval 1 and 2. Now again, if your calculator does not have that, you have to use the computations and you have to do the hard way. You're going to do the definition of this, the formula of this, and you're going to just plug in the 2's and the 1's. Remember, when you're using the calculator, you're looking at this function over here, the natural log function, and above this you have this e to the x. So you have to do shift and hit this button, which will activate this e to the x. So let's do this over here and get the numerical value. Over here I get 1.1752. Now let's do this one over here, again working from the right to the left because it's easier that way. 3.626. When you minus this other answer from it, we'll get our eventual numerical answer, and it will be 2.45, let's round it up, 2.452, and that'll be your final answer, and it would be right. Now this question over here should not pose any extra challenges. You just have to use your reference sheet, or from your memory you can play this out. Tan hx, the antiderivative of this, or the integral of this, is natural log cosine hx over the interval 3 and 2. There's no plus c because we still have to calculate it out, and this is how you'll do it. You'll do natural log cosine h of 3, right, minus natural log cosine h of 2, because where the x's are being replaced by these numerical interval, upper limit, lower limit. And in each of these cases now you have to plug them into their definitions, because my calculator does not have the simple hyperbolic function buttons on it, but that's fine, I'll have to work around that. You will put e to the power of 3 plus e to the power of minus 3 minus natural log over here e to the 2 plus e to the minus 2 over 2. Basically what this is saying is e to the x plus e to the minus x over 2, where the x's are replaced by these upper and the lower limits. Now we have to actually solve all of this out. Let's solve it out. We'll put answer here, and we'll get the final of 0.98. Let's just keep it to 3 digits. 0.984, and that's your final answer. So we'll try to have some fun over here by looking at some indefinite integral questions with regards to hyperbolic functions. Where and when possible, we'll have the appropriate antiderivative listed over there on the side, so it can help us guide through the question. Look where it's a composite. If u is equal to 2x squared, then du is equal to 4x dx, and dx is equal to du over 4x. Utilize this right in this form. Secant hu du over 4x. These x's can cancel out. You can bring the 1 over 4 out, and you essentially end up reducing the entire expression to just a single function, which will follow in that scheme of antiderivative. You'll have 1 over 4, you'll have arc tan, and you'll bring in the sine h as you're following, and the x will be replaced by the u, and the u will be replaced by the 2x squared plus c, and that'll be your final answer. You could take the derivative of this entire expression and you could end up right over here. Take a look over here at this function. You have a hyperbolic cotangent. The basic integral for the hyperbolic cotangent is shown right over here, as was previously shown. A composite over here, u is equal to e to the x plus 1, du is equal to e to the x dx, because the derivative of e to the x is just e to the x, it's easy. Dx is equal to du over e to the x, and we're kind of limited here in terms of the questions I can show because of our lack of knowledge of the advanced substitution techniques. I haven't presented those, therefore it makes no point in me presenting examples involving those complex maneuvers. We have to stick with the basics here for right now. We will stick with that, and we have hyperbolic cotangent h being replaced with the u, and then du over e to the x. The e to the x's will cancel out, so you just end up with basically the hyperbolic cotangent in form of u. You'll go into that step over there, natural log, you'll do sine h of u plus c, but the u has to be replaced by what the actual substituent is. The substituent, u is e to the x plus 1, right? E to the x plus 1 and plus c, and this right here represents your final complete answer. Well, let's look at this question over here. You have secant h, x plus 3, hyperbolic tan, x plus 3. Anything which looks like this, secant hx, tan hx, you're doing the integral of something like that. The antiderivative is minus secant hx, mirroring very well what the trigonometric version of the same integral is. We have to do substitution technique here. U is equal to x plus 3. Du is equal to just dx. The next step is easy. You're basically having this, and then du over here. Nothing came out over here, nothing needed to be cancelled. You're just following this integration now using that scheme. Your eventual answer is, when you do the integration of this, you get minus secant h u plus c, but you have to resubstitute back what u was. Minus secant h x plus 3 plus c, and this represents your antiderivative function of the original function. This is an easy question, but not a hard one by any means. Anytime you're seeing the integral, which looks like a cosecant hx, cotangent, hyperbolic hx, these are hyperbolic versions, hyperbolic cosecant and hyperbolic cotangent. Based on the 10 integrals I showed you with regards to hyperbolics, this right here would represent the antiderivative. You have to substitute here for the composite function. U is equal to cosine x, and then du is equal to minus sine x dx, and then dx is equal to minus du over sine x. You can just bring the minus across right over here, it's alright. Cosecant hu, cotangent hyperbolic u, and then du over sine x. Let's not forget the minus, and we'll bring it right over here. We can cancel this out. We are essentially seeing this now. If the positive versions will give you a minus that antiderivative, the minus this integral or the pre-integral will give you a positive antiderivative, because the minuses will cancel out. Your answer will be here cosecant h u plus c, and you have to resubstitute back for the u. Cosecant h cosine x plus c, and this right here is your final answer. You could take the derivative of this antiderivative and you could end up back to where you started. This will prove to be an interesting question because this type of function, hyperbolic function, is not very frequently seen in questions. So anytime you see them, it gives you an opportunity to apply the integration for this. Here's the antiderivative of something which would look like a basic hyperbolic cosecant function. You know, we are looking at a composite over here, and we have to treat it as such with a basic polynomial substitution. U is equal to 2x, and then du is equal to 2dx, and dx is equal to du over 2. We have to come over here to this step and plug in the u, and then the du over 2. The over 2 can come out always on the side. It's not a bad idea. Anytime you have a coefficient, you bring it outside. Whether it's a derivative or integral question, just bring it outside. So we just have to follow the scheme of this. We bring a 1 over 2 outside as we do, and we have natural log. Then we have to do the tan h x over 2, but it's really a u over 2, isn't it, right now, plus c. We're not done because we have a u over there when our final answer must have the x in it. So we have a 1 over 2 natural log tan h, what was a u? It was a 2x over 2. 2x over 2 plus c. We can still condense this, simplified algebraically, such that our final answer would be 1 over 2 natural log tan h, and you can just put an x over here and then plus c. You see the 2x over 2 simplified to the basic x. The 2 is cancelled out, and that right here is the final answer. We have to just do integration here. Hyperbolic functions here we have in front of us. We look at a composite which is right here, and we do a substitution. If u is equal to cosine hx, then du is equal to sine hx dx, and we always solve in this case for the dx. You come right over here. We have sine hx, then we have u squared because this u comes right here, and then du over sine hx. These will easily cancel out, so you only have u squared du left, and this is just a polynomial integration right over here. This will be u cubed over 3 plus c. When you resubstitute back, you get 1 over 3. I'm just bringing the 1 over 3 out as a coefficient, and you get cosine h cube x plus c, and this represents your final answer. You can do the derivative of this and you'll end up back easily over there. No problems. Now in terms of form and substance, this question is no different than the previous. Here's our composite aspect. We substitute for the composite. U is equal to 1 plus 4x. Du is equal to 4dx. And then dx is equal to du over 4. We bring our substitution right here onto the integral we're looking at. We have sine hu and then du over 4. You can bring the 4 outside as a coefficient of this entire integrand. You'll have a sine h u du, and you know this is easy. This is just cosine hu over 4 plus c, and we can resubstitute back to get our final answer with this substitution here. We'll have cosine hyperbolic with 1 plus 4x in the parentheses all divided by 4 plus c, and that is our final answer, the antiderivative. For this question here, it's clear what the substitution should be. It's root x. U is equal to root x, and then du, you know, every time you see something like this, it's always 1 over 2 the square root of whatever radical we were looking at, variable within the radical. So dx is equal to 2 root x du. Here's our substitution, and here's our substitution, which will affect this sine hu. The 2 can come out right here at the beginning as a coefficient. We'll have root x du, and then root x on the bottom. These root x's cancel out. So from this step, the next obvious step is just taking the sine hu, which you know is cosine hu, and then plus c, because these are all indefinite integrals. You have to resubstitute back for this u with what you see over here, which leads you to your final antiderivative, which is cosine h root x plus c. And this right here is not a hard question by any means, and it's done. For this question over here, this can prove to be quite tricky if it's not handled properly. If you start just looking at this over here and start making substitutions based on this, you might end up going down a track which you cannot complete based on the techniques you know. You have to basically view this in terms of an identity which you have been introduced to. Cosine h squared x minus sine h squared x is equal to 1. If you bring the 1 on this side, 1 over here, and you take the sine h squared on the other side, what do you get? You get cosine h squared x minus 1 is equal to sine h squared x. We're substituting this for this right over here, and there's nothing wrong with you doing that. So you're looking at the question now in terms of this. You can always do whatever manipulation you want to do prior to doing your substitution technique. Now you know easily what you should do as a substitution with. It's sine h. If u is equal to sine h x, du is equal to cosine h x dx, and dx is equal to du over cosine h x. You just do the substitution over here. You get a cosine hx here on the top, which you already have. Here on the bottom you have u square. Remember u square, and then du over cosine hx. What you end up with is basically du over u square, or u to the minus 2 du. You can bring it up, make it easier. And now you do the n plus 1 divided by n plus 1. Remember the basic polynomial integration technique? That's all what you do. You'll get u to the minus 1 on the top, you'll get minus 1 on the bottom, plus c. Well, you get, after you substitute, you know u is sine hx. You'll get a minus 1 over sine hx plus c, which you can write in a better way. And I'm going to make that space over here, because you know this is the reciprocal of a specific function we know. Let's erase this over here and bring our final answer right here to the side. Minus 1 over sine hx plus c is the same thing as saying minus cosecant hx plus c. And this right here is your best answer. So with this question over here, we will end our video. When you're looking at this denominator over here, roll with that as your substitution, because this can generate something which can cancel with secant h squared x. If you look at it in this way, u is equal to 2 plus tan hx, then du is equal to secant h squared x dx, and then dx is equal to du over secant h squared x. This right here will be our substitution, and this right here will be our substitution, which will play right in over here. We'll have secant h squared x du over secant h squared x over u. Remember, this 2 plus tan hx is over u. These cancel out. What you end up getting is u to the minus 1 du, because you can bring the u to the numerator and it comes out as a minus 1. Remember, it's 1 over u, which in exponential form is a u to the minus 1. And anytime you see this in terms of exponential integration, you're thinking about natural log. You're really thinking about natural log u plus c, which will translate into natural log 2 plus tan hx plus c. Just to make sure that we are indeed here on the right sheet of music, we should take the derivative of this to see if we end up with that, and we can conclude our video with that last technique. We're going to take the derivative of the antiderivative to end up back with the original function. You know, this right over here is going to be a composite involving the chain rule. If d or du is ln u, and then du over dx is equal to this item in between, 2 plus tan hx. We'll basically get 1 over u over here, and derivative of this constant 2 is a 0, but derivative of tan hx, and I can refer here to my reference sheet, would be secant h square x. It is a secant h square x. I get a secant h square x. When I substitute back for the u, I keep the numerator as I'm seeing it, secant h square x, but the u was 2 plus tan hx, right? 2 plus tan hx, and here is our function. Because here our substitution was, if u is equal to 2 plus tan hx, then function with regards to u must be ln u, natural log u. And that is how we played this entire chain rule over here. And you know, the chain rule is so commonly seen that it's second nature to us. But this question is done. My antiderivative is right over here, the natural log, parentheses 2 plus tan hx. My derivation of the antiderivative, going back to the original function, is right here at the bottom. This entire procedure over here. And that concludes our video. I hope you enjoyed this video on hyperbolic integrals. Just don't be surprised if you don't see too many of these questions in your classwork, because you just may not. I hope you enjoyed the video. Please stay tuned because there are many more videos coming up. Thank you for watching. Have a nice day. Bye.